Hello and welcome to C++ Weekly. I am your host, Jason Turner. I am available for code reviews and on-site training. I am also planning to give upcoming talks and workshops at NDC TechTown in Kongsberg, Norway in September of 2024. And I suggest that you check that out if you have interest in coming to one of my workshops. In this episode, I'm going to talk about the mold linker. Now, if you have paid attention at all to linking technology lately, you are probably aware of mold and aware of its claims to super fast link times. And I have this animation playing in the background here, which you may have seen from Mold's GitHub repository, where they are demonstrating the amazing parallelization possible with their linker compared to the other alternatives. So I did my own experiments, and this episode has been well over a year in the planning as I've tried to decide the best way to demonstrate this. And for this particular case, I am actually using Mold with that same project that I recently showed you with Unity builds. So we can kind of see how some of these things compare, what impact Mold had on this particular project. So the first thing that you need to be aware of is that, well, your compiler uses linkers. So our compilation process with C++ is typically that multiple CPP files are compiled into multiple object files. Then those object files are linked into our executable shared library .a static library. And this is the same across all of the different platforms. It is going to be something like that. Now, if you have projects with very large libraries, you might notice that you spend a lot of time linking. And this can particularly be a problem if the linking is a bottleneck in your build process. If you've got some sort of intermediate libraries that later parts of your project rely on, there's a good chance that you're going to have a bottleneck where you'll have a bunch of CPP files that are compiled, then they'll all be linked into one library, and you have to sit there and wait for some time until you have that linked, and then you can start building the next chunk that relies on that library. Now, as an aside, I have personally spent a lot of time going through and hand tweaking build scripts to remove artificial dependencies between libraries in my project, which ended up drastically increasing the parallelization of my build and reducing the amount of bottleneck wait times that I had. But if you have very large libraries that need to be linked, they can take a considerable amount of memory during that linking process, and depending on how much memory you have available on your build system, you might end up actually causing a new type of problem where if you are overly parallel, if you will, then you don't have enough memory to continue compiling one thing while linking another, or to link very large things all at the same time. That's definitely an aside, just something to consider while you are looking at your own build times in your own projects. Okay, so we have Mold, and it is for Linux primarily. If you want to use this on Mac OS, then you need to use their commercial version called Sold, S-O-L-D, and this is Mold, M-O-L-D. And they've got this demonstration graph here showing that with GNU's Gold linker, you are taking 60-ish seconds to link Clang 13, for example. And with LLVM's LLD, that is the alternative linker available from LLVM, then you're taking 5.8 seconds, and with Mold, you've cut that time in half to 2.9 seconds. Now, these are very large binaries. Clang 13 is a 3 gigabyte binary. That takes 64 seconds to link, and with Mold, it takes 3 seconds to link. So just set your expectations appropriately. If you don't have currently a bottleneck at link time, then you're not going to see as big of an impact. GCC has this -fuse-ld, and you can just straightforward. Simply choose between BFD, gold, LLD, and mold. If you've got a recent version of GCC, it's really simple to just pass this -f use -ld. And I can show you here that in my own CMake project where I was experimenting with this, I just pretty straightforward created a new property, cached property called useLD. I gave it the options BFD, gold, LLD, and mold with a default option of an empty string. And empty string uses the default. And then I say, if it has been set, then pass this as a link option to GCC. It's really just that straightforward. Now, Clang also has the -f use -ld, and it doesn't specify if it's limited in the particular types of linkers that it can use here, so you're just going to have to experiment with that on your own. Now, of course, the thing that you're curious about is my actual results from having done this experiment myself. So I'm just going to pull up the results that I already have published on my GitHub repository. Now, for my particular project, as my notes show here, I saw about 3.5 times improvement for my largest link time. And so, like linking a debug build that might be slower to link, for example, you might actually see more improvement. But I also saw this gigantic memory usage improvement. And this is going to speak back to the comment that I made before that it's possible linking itself is not necessarily your bottleneck, but perhaps linking several large things at a time and consuming a large amount of memory is your biggest problem. And mold might be able to help you out there. This project was taking 20 seconds to link. This is just the link time, and I am linking with gold. And when I linked with mold, I got a 6-second link time for debug build. Now, an interesting note is that mold consistently produced larger binaries before stripping, and I did use Bloaty McBloatface to actually analyze this. And I did an episode on Bloaty previously. You should maybe check that out. But I used Bloaty here, and it appeared that I was getting more unnecessarily exported symbols in my shared object file with mold than I was with gold. But with stripping, they ended up about the same size. And if you want to come in here and look at all of the raw data for the various things that I tried with both gold and mold and LTO on and LTO off, you can check those out. Now, keep in mind, I've done other episodes on link time optimization. If you are using LTO, do not expect as big of a potential improvement because LTO, link time optimization, actually does the translation from intermediate representation to an actual object file executable code at link time. So it's having to call out back to your compiler to generate optimized binaries instead of just being able to parallelize all of the actual link operations. But I definitely saw some difference in all cases. But for this particular project, link time was not nearly as big of a bottleneck as I thought that it was. If the thing takes many minutes to compile and I get a 14-second savings, then I'm probably not going to move my whole workflow over to using the new linker. But it is definitely something that you can play with. So again, on GCC and Clang, this is easy. Go ahead and play with it. See what you think. Report in the comments what kind of experience you have had with mold, or perhaps what kind of experiences you have had with very long link times. So thank you for watching this episode of C++ Weekly. Hope you learned about a new tool. And also, you should use Bloaty to analyze the binaries that come out from your different linkers to see if you see the same kind of weird discrepancy in linked sizes like I did. So I'll catch you in the next episode.